let's do some hand calculations of expected results. And in doing hand calculations, what is important is not to find a formula and do some plug and chug that can be meaningless if we don't understand what's the backstory. So we will focus on the backstory behind the hand calculations and compare it to the backstory behind the ANSYS calculation. If I go to the framework of what's inside the black box, we have looked at the mathematical model, we have looked at the numerical solution strategy used to solve it to get displacements at selected points, i.e. the nodes. So we are moving on to doing hand calculations. And let's compare, the mathematical model used there to this mathematical model. So here's a physical problem, torsion of a cylindrical shaft, and I have reproduced the schematic from the problem statement here. And we saw that in the finite element approach, you are looking at the boundary value problem and based on the equilibrium equations, and using the finite element method, we can get a solution, a numerical solution that's approximate, and get displacements at the nodes. And we saw what are the errors introduced in that process. And then once we have displacements at the nodes, we can interpolate those displacements and get the displacements everywhere. And once we know the displacements everywhere, and the interpolation happens element by element, and so once we have the displacement field, element by element, we can construct the strains and the stresses. So let's compare that to the hand calculation approach, where you start with assumptions. So this is the hand calc approach. And you make two key assumptions. The first assumption is you say, if I look at a cross-section like that, that's just going to rotate like a rigid body. So if I take a point there, that's just going to rotate like that and end up here. And I'm exaggerating the amount of rotation. So let me write that down. So you'll say each cross-section rotates as a rigid body. And the second assumption you make is that the amount of rotation varies linearly along the axis. What this means is if this cross-section, say, is halfway along the shaft, then it will rotate half as much as the cross-section at the end. Now, with those two assumptions, we can essentially construct the displacement field in terms of the rotation, or rather the rotation per unit length. So this theta is a rotation per unit length. Now, since plane sections remain plane, and that's an assumption built into that, the displacement in the z direction is 0. Z is along the axis, and then the displacements in x and y can be constructed from the amount of rotation. And the amount of rotation is the rotation per unit length times z. Okay, so you get something like that, and I'm following Borisi and Schmidt. And you can actually find this a copy on the internet for free, and I believe it's even legitimate, and that this is chapter 6. And once we know the displacements, we can calculate the strains and the stresses. And you can actually go on to show that actually this is a solution to this boundary value problem with one restriction. We need to have the twist or the torque being applied such that the stress distribution matches that. And but anyway, when you're away from that end, you expect that the displacements will match that, and then by calculating the stresses from this and looking at the stresses on that cross section, they should add up to the applied torque. And if you do that, you will get theta equals T over Gj, where T is the applied torque, and G is the shear modulus, and J is the polar moment of inertia. And Barisi and Schmidt shows you how to do that. And then, ultimately, once we know the displacements, we can calculate the shear, which is the only, there's only shear, there's no normal stresses, and the shear comes out to be TR over J, which means it's going to vary linearly along the radius over any cross section. So that's something we can check in the ANSYS solution. And so since this is a solution to the boundary value problem, with the moment applied a particular way, we should be able to look at a cross section and check these assumptions. If that cross section just rotates as a rigid body, and we can also check if the amount of rotation varies linearly. So we will do that in the ANSYS solution.